Okay, good day, viewers. You are welcome once again to MOG Economics YouTube channel. Now, in today's class, we are going to be looking at another interesting mathematical concept that has a very useful application in economics, and that is the first-order differential equation. So, in our previous classes, we have been introduced to a number of mathematical concepts, and then we try to also look at the applications to economics. Now, in the very first class, I made us understand that the basic usefulness of this mathematical concept the application basically to economics. So we are not just looking at this concept they are for looking sake, let me put it that way. But we want to see how we can apply this concept to economics. So that's basically what we are doing. And in today's class, we are going to be looking at the first order differential equation. Now, what is a differential equation? Now, a differential equation expresses an explicit relationship between a function and its derivative or differentials. So, what do we mean? It expresses an explicit relationship between a function and its derivatives or differential. Now, there are instances where the relationship we are expressing may be implicit. Now, if you look at the first case here, this is um, basically talking about the rate of change in y with respect to time. This is the function. It shows that rate of change in y with respect to time is 5 plus. So this is just different forms of expressing differential equations. These are like different forms. The first one, this is a first order. This is also first order. This second, but this in this case, this third equation is implicit. The way it is structured, I believe from your previous classes on differentiation must have been introduced to the difference between explicit and implicit differentiation, stuff like that. So in this case, this function here is expressed implicitly. Now, the ordinary differential equation. What do we mean by the ordinary differential equation? The ordinary differential equations are equations with single independent variable. Now, we are talking about just single independent variable. So note that looking at our focus is on single independent variable and nothing more than that. So now the order of differential equation is, now we need to get familiar with some terms here at this point. Now we need to get familiar with what we mean by the order of a differential equation and the degree of a differential equation. Now what do we mean by the order of differential equation? Now the order of differential equation simply is the order of the highest derivative in the equation. The order of the highest derivative in the equation. Don't worry, very soon you get to understand what we mean by that. Now we have the degree is talking about the highest power to which the derivative of the highest order is raised. The highest power to which the derivative of the highest order is raised. Now let's consider these equations. These are differential equations. Look at these equations. Now the first one here is the first order and first degree differential equation. Now look at this. This differential is of first order and it is to the first degree. What do we mean by degree? That is, here, this first order differential is raised to the power of 1. In this case, it is left out since it can still be expressed as the y over dt. So there's no point including that. But you just have to understand that this is the first order differential and is raised to the first degree. Now, looking at the second one here, we have this. The highest order of differential here is order 1. That's the first order. That's the highest order in this case. Now, this first order, which is our highest order in this case, is raised to the power of 4. So the degree here is to 4, is raised to the power of 4. Meaning, here the highest order differential we have here is just 1, and it is raised to the fourth degree. So this differential equation can then be considered as a first order and fourth degree differential equation. Now, the third one here it can easily be seen that the highest order differential is 2. Yeah, so it's a second order differential equation, and it's of first degree. Now, going back to our definition of degree of differential, it is clearly stated here that the degree of differential equation is the highest power to which the derivative of the highest order is raised. So the highest order in this case is order 2, and it is raised to the power of 1, just like in this case. Here we have decided to leave it out. There's no point in including that. It's raised to the power of 1. Now, for the last one, here the highest order is order 3. This, and then it is raised to the power of 5. That highest order in this case is order 3 and it's raised to the power. So this differential equation is of third order and fifth degree. So in case you see something like this, you should be able to identify the order, and you should tell us, okay, this particular differential equation is of this social order and it's of this social degree. Very quickly, I think I have to clarify something at this point. Here, some might be wondering why we do not say, okay, this particular differential equation is of, say, order this, and because here it is raised to the power of 3, then we should say, okay, it is first order and then third degree or something like that. But in this case, going back to our definition of order and degree, we need to understand that the degree now is determined by the highest order differential in the equation. Now, looking at this now, this differential is the highest because it's raised to it is to the second order. Now this is to the first order. So even though it is raised to the power of 3, we won't pick this, we won't consider this, we are considering this because this differential is the highest, or it's the highest we have in this equation. Okay. So it is of the higher order again. Okay, let me see. This is of the highest order here. We are considering this because it is can be differentiated twice, and that's it. So now going further, at this point we would like to consider the general formula for first order linear differential. Now I want us to, just like we have done in the previous classes when we're treating even concept, the Taylor and Maclaurin series, those concepts, the difference equation. At a point we came up with a particular general formula for each of them. So for those topics we have treated, you need to know there's something common to all of that. That's the general formula. So, and this you need to commit those formulas to memory. You really need them. You need those formulas to solve. And at this point here, we won't really bother as much about the derivation because here the focus is the application to economics. So we won't really bother much on how those general formulas are, for at least for this level. So now, general formula for the first order linear differential equation. Now, let's consider an equation. This is a differential equation. Now, this is just like though in this case it is implicit. This is implicit. This is a kind of implicit function. Now you have the dependent variable appearing on the left side and independent on the right. So I believe from your classes on differentiation you must have been told something like that. So here, where v and z will be constant or function of time. Now this v and z, they may be constant. Now constant, I believe at this level you know what those terms mean. For constant, it doesn't change, and it could be a function of time, like either as v or z will be a function of time depending on time. Now this is the general formula. A given function, arbitrary function. Now for an arbitrary function, this is the formula. So here, this is the natural logarithm raised to the power of negative. Now this It's an integral sign, so it appears also here. This is the v. From this equation, the v, it also appears here in the formula. Then this is the t. Then yeah. So now this formula, there are terms here, and I want us at this point to consider them, to be familiar with those terms, the symbols. Now, here the first thing is the A, this letter in the bracket. So it is the arbitrary constant. We refer to it as the arbitrary constant in this case. It's the arbitrary constant. Now, here, now this equation is actually divided into two parts. Just like we did in the case of the difference equation, where we have one part of the equation talking about the deviation of the equation from equilibrium, from intertemporal equilibrium, and then the other part which is talking basically about the equilibrium. Now the same thing, we have the same thing here. One part of the equation is talking about the deviation from a given equilibrium, because here, just like we did for difference equation, we'll also be looking at stability condition, the state at which a given equilibrium, particular equilibrium, is considered stable. And I believe at this point you know what I mean by stability. So stability, basically, just a quick recall, stability is talking about the ability of an equilibrium state to be restored once it is disturbed. Like once there's any factor, outside factor, anything that causes a particular equilibrium state to be disturbed, forces will bring back that state. So now, this is the arbitrary constant. Now, this first part, which is this, so when if we expand this bracket with this term here, that is this first one, this is the um, the complementary. These are complementary equation, or let me, more appropriately, I want to use the appropriate word here. Okay, let's say it is let's call it the complementary function, which we will refer to as yc. Then the other part, so this is the particular solution, or the particular, here in this case it is referred to as particular integral. Now in the case of difference equation, we called it the particular solution. In this case it is the particular integral, and call that yp. Alright, so now, just like we were made to understand in the case of the difference equation, now for this differential equation to be stable, as our time approaches infinity, this, as time as we go forward in time, as we move forward in time, as time approaches infinity, this equation will approach this, to approach our intertemporal equilibrium. Now this is the particular integral, which is also our intertemporal equilibrium. So as the time tends towards infinity, this differential equation would tend towards the equilibrium, because this will gradually approach zero. Now at this point, so just to bring clarity, I would like us to consider a practical example. Now this is a differential equation. This is an equation. Now we have to express the general solution of this, yeah, for the equation. Now this is the general formula. Now we are to use the general formula in this case to solve this and see if our general formula is an exact equation for this, if it is exact or if it's just an approximation of this. So here we have this looking exactly like this, so it's just like this. So in this case, clearly we can see that our v term is 4. Just following this equation we have here, the v is 4 and z is 12. So now we can apply our formula. Okay, so applying our formula, we have natural exponential, yes. Okay. Our integral sign, then the v in this case, which is 4, then we have here, I need to clearly, okay, retain, okay, retain, and then the integral sign again. This our z from here is 12, and the exponential again, and the v 4. So integrating this again. So here we have, okay, so by integrating this, we have this, then this becomes minus 40, then here this okay, we can just have this. So here again we have 4t, then we will still retain this. So this goes out, this is already integrated, so this goes out of it. Then this applies to this, the whole of this. So here we are integrating this again. Now we have, so here, in order to integrate this, we use the substitution, integration by substitution, yes. So in this case we have, oh, I'm sorry, I am supposed to have the integral sign here. We left it out. This is supposed to be here. So now we are integrating this part. Now this is the result. Now how did we get here? This is integration by substitution. So let's say we have 12. This is 12. We are integrating this 40, then this. So we can just easily have our this value here out of the integral sign. Then we have this for simplicity. Now we have this power here. We are substituting. We are using a variable in place of that. Let's say u in this case as a representation for this. So when we differentiate this, we have this, which is 4. So here the inverse of this is or from here our dt, we are making dt the subject, is 1/4 du. So we make dt the subject from here. So we have this. Then this, what we have here, we are substituting here. So then our result becomes this. So since this integral sign won't be there any longer, since we have integrated already, and then we have, okay, let's do u, this, we are replacing this, so we have 1/4 du. Alright, so here, from here, our u is 40, and then from here we can solve algebraically. We have this, there's this, raised to power 40, or in this case, plus the a constant term. So here this becomes 3, and then we have 3e raised to the power of 40 plus 6. So usually when you integrate, you leave an arbitrary constant at the end, because now it's an indefinite solution, and then the constant term is not known. So, but in this case, we are not leaving it here. We have, in this case, a specified term in the case of this equation, which is referred to as the arbitrary. So it is defined in the formula. The arbitrary constant is defined in the formula already. So we are not introducing this term in this case. So just after solving, this is just standing in as an arbitrary constant. So from here, this, so this is exactly how we got this. Now, so from there, we have, let's continue from there. We have this, a natural minus raised to the power minus 40 into the bracket a plus, now that is 3e raised to the power of 40. Alright, so we have this. So now from here we have, now this is, let's open the bracket, let's expand the bracket with this. So we have n plus, so from here this becomes 3 multiplied by, so here we have, now from here this becomes 3. And how did you get that? Here, this 2, here we can easily apply the law of indices, because here they have the same base, the natural, the exponential is the same, and then we can easily add up the powers. So, and the law of logarithm says when you have, when the bases are the same, and they are separated by a multiplication sign, you can easily add up the powers. So in this case, we have this 40 plus, which eventually becomes minus 40. So this is e all raised to the power of 0, and this is applying the law of indices again. This is 1. So, and that's exactly how we got this. 3 times 1 is 3. Now this is our answer. Now this two parts, this part is the particular integral. From there, our particular integral, this is it. Then this is our complementary function. So this is like the deviation, and this is the particular integral. This is like the equilibrium value. Now this, as this tends to infinity, this tends to zero as we increase the value of this. Because okay, let's look at it this way. If this t increases from 1, 2, 3, this expression, this is inverse of 40, that would be 1 over e raised to the power of 4, and then you continue to increase like that. Then this keeps getting bigger and bigger, and then this whole expression rather will continue to decrease, and then this will approach this whole term here will approach zero, and then until this our function in this case, until this approaches 3, which is our particular integral. So that's only when we can consider this differential equation to be stable. All right, so at this point we are going to uh, look at the exact differential equation and partial integration. Now, I've been talking about stability condition. We have been introduced to the term of deviation and particular integral. So at this point we are looking specifically into what we mean by the deviation or the complementary function and the particular integral. We want to see what we mean by that, and when a particular we want to know when a particular differential equation is an exact approximation or just a deviation and not an exact. In the next class, we are going to be looking basically at that. So see you there.